Good afternoon. So today we have a big moment in the sense that we're going to go over one example of solving from top to finish a boundary value problem, a homogeneous boundary value problem. Often in some cases, I prefer to actually solve a full example slowly from beginning to the end, preferably an example that covers as many particular cases as possible so that you have an idea, an overall idea of how the method works. So rather than giving you the blueprint, the entire map of how you're supposed to go over this method, I prefer to actually illustrate the method first with an example, and then we're going to have plenty of time to discuss the method in the general setting, to obviously go over different types of examples and to see many differences that can happen. But because this is our first example, the lecture will be probably longer than you might expect for a single problem. And this is intentional because I want to go slowly and discuss lots of steps and, and to make lots of remarks along the way. And be patient and go with the same slow pace, because once you get the main idea of how the method works, this is pretty much all we're going to do from now till the end of the course. The only difference is essentially the tools that may happen. We're going to need at some point different type of series like Bessel or Legendre, but the overall method is the same, namely the method of separation of variables. And again, some portions of the solution might be skipped if they are repeated. Like, for example, a big portion of the solution may be taken for granted later on if we recognize it from other problems. So it's not like all the problems will be that long. This is intentionally done from top to finish, discussing every single item, just to be aware of all the parts and their significance, so to speak. So if you cannot do this in one sitting, just split it into two sittings if you prefer, because I don't know how long it will take. Probably close to an hour, we'll see. So I'll choose before we talk about the method itself, or the example itself, let me make another remark. Well, first of all, let's remember what we covered in the previous lecture. If we have a homogeneous boundary value problem, if you find a bunch of solutions, infinitely many of them, for example, which you'll see it can happen and it's good that it happens, then a linear combination, I forgot to mention here an. So any linear combination of them is also a solution. So the summation from 1 to infinity, an, un. So let me write it one more time. So e1, u2, un, if these are solutions, then of the same PDE, then a linear combination of those is also a solution. And notice that at some point, if that solution is going to be in that format, the question is to find those coefficients, and we'll get to that in due course. And another remark, which is surprisingly easier to grasp, although that's the key thing for the method. If I give you two functions in terms of two different variables, so let's say you have two functions, let's say f of x and g of t, and I tell you that f of x is equal to g of t for any x and t, then both must be constant, must be a constant, and it has to be the same constant if they're equal to each other. Because if you have two variables that can vary independently, that's the key thing here. If they vary independently, so if these two functions are equal to each other for any x and t, well, for example, you can replace t with 0, or with any real number for that matter. So that means f of x is equal to g of 0, which is a constant. And then you can, of course, repeat and that would be true for any x. And then you can repeat the argument by saying g of t must be equal to f of 0 for any x. But then if they are equal to each other, then f of 0 must be equal to g of 0. So therefore, it follows that the two functions really must be equal to the same constant. This is a quick proof. It's not that important for later. It's just important to understand that it's not actually a big result, so to speak. It's just essentially an observation to make that if we do have two functions that can vary independently, each with its own variable, x and t, the only way for them to be equal for any x and t is to be equal to the same constant. Nothing special about this zero, by the way. Again, you can essentially fix one of the variable and then the other one must be equal to that constant. So all of a sudden you just proved that f of x is a constant. You can repeat the argument for g of t, so that must be a constant as well. So therefore these two must be equal to each other, again, if we know from the beginning that they must be equal to each other for any x and t. So we have this remark, and you will see that the essence of the method of separation of variables is, as the title implies, we can separate indeed the PDE, the given PDE, into the equality of two functions, although those two functions will contain derivatives. So, but view it as functions with respect to each variable involved. They will be equal to each other and they must be a constant. And that essentially allows us to split the problem from a PDE to actually two problems, each of which are ordinary differential equations. But without further ado, let's actually formulate the problem to solve, and we'll go slowly and see how this plays out. And I'm going to choose our first example. So our first boundary value problem to solve. I'm going to choose a wave equation with the elastic coefficient equal to 1, just to make it as simple as possible. So u partial t twice on the left equals u partial x twice on the right. And we're going to have an initial displacement. And by the way, let's say x is between 0 and pi. That's kind of a strange length for a vibrating string, but I'm choosing that interval so that the series that I'm going to need are the easiest one to deal with. And we're going to have some initial displacement, y of x0 equals x. We're going to have an initial velocity, and let's make it 0. And we have 0 boundary conditions. So basically, for the method to work in the beginning, we're going to need essentially homogeneous condition except one. We can still have one condition which is not homogeneous, which is the initial displacement. All others should be homogeneous. So y of 0t, let's say, is equal to y of pi t is equal to 0. So those indicate that the string is fixed at those two endpoints. So again, if we visualize what goes on here, the string in its non-stretched position is along the x-axis. And imagine these are some fixed poles at 0 and pi. This is the string when it's not stretched. And then at time 0, initially we're going to stretch it vertically so that it's going to be like that. I'm kind of going over the writing above here, but imagine you stretch it vertically right above the right pole, so that the displacement is given by x, right? So the equation of this line is just y equals x. And then you let it loose, because the initial velocity is going to be 0. So basically it's going to snap back probably along the vertical line, and then it's going to vibrate. And the idea is to find the equation of the displacement at time t, at each point x on that vibrating string. So the boundary conditions y of 0 t, y of pi t equals 0 indicate that the string is fixed at the endpoints. Stretch vertically so that the shape of the string follows the equation y equals x. Then you let it loose because there's no initial velocity. And then we have to find the equation of the motion. All right. So with that out of the way, let's actually proceed with what is going to be actually the application of the method of separation of variables. So we simply assume that the solution of the boundary value problem can be written as a product between a function in x and a function in t. So we assume that this solution is separable in this sense, right? A product of a function in x and a function in the time t. So by convention, we can denote this function in x like big X of little x, and the function in terms of little t, big T of little t. If we can separate the equation, then we arrive to a separable equation essentially, and then we can proceed with the method further. Now, in order to plug in this format into the PDE, so if we assume that y of xt follows this format, then we must plug it into the PDE so we can figure out some equations in big X and big T. Now notice that y partial t twice, that's going to be big X of little x t double prime of t, because big X is a constant. I mean, big X of little x is a constant with respect to t. And partial x twice of xt is going to be x double prime of little x times big T of little t. And now let's plug this into the PDE. So we have on the left side y partial t, and on the right hand side x double prime of little x big T of little t. This is the part that may be a little bit unpredictable in the sense that can we separate it in terms of x and t? In other words, can we rearrange the terms so that on one side of the equality we have only t, functions of little t, and on the other side of the equality just functions in terms of little x? Most of the time, if the equation is separable, it's pretty obvious how the separation works. And I would advise you to keep the derivatives on the top. So for example, leave the x double prime on the right, but divide by big X, and also divide by big T. I forgot to mention something, but I'll get to that immediately, because remember you can divide by 0. But let's do this separation. So notice if I rearrange the terms, divide by big T, divide by big X, then on the left side I'm going to have t double prime of little t of big T, and on the right hand side x double prime of little x over big X of little x. I forgot to mention that we assume that big X is not equal to 0 for any x and big T is not equal to 0. We're looking for non-trivial solutions. So we're not looking for this obvious solution, which is 0, right? Obviously, if I plug in 0 for y of xt, that's a true solution. That's the equilibrium solution when the, when the wire is relaxed between the two poles, right? But we're looking for non-trivial solutions that correspond to the motion in time t. So we're going to continue on the next page, and I'll probably copy the problem again and this last piece here, and we continue the discussion, so stay tuned. All right, so let's continue. So the problem is on the corner here. We assume that the solution has the product form, function in x times function in t. We arrive to the conclusion that the equation is separable, and this leads to this equality. T double prime over t equals x double prime over big X. Because of the observation we had before, then these two must be equal to each other. I mean, they are equal to each other, and they must be a constant. Because if this is true for any x and t, then both must be equal to a constant. So this is the time to introduce what is called a separation constant. To use the tradition of notations in problems like this, denote this constant by minus lambda. You'll see immediately why we put that minus out. It can be really any notation here, but just name it for now minus lambda. You might guess that you'll see later that lambda, at least in this problem, actually is going to be a positive number. So in anticipation for that, we're going to keep the minus out of the constant, of the separation constant, again for convenience. There are lots of conventions like this just for aesthetic purposes, so to speak. Again, we know that they must be a constant. Let's just name it minus lambda. And then, of course, at some point, lambda must be found if we were to actually solve these equations. So pay attention now what goes on with our problem. With this separation, when these two are equal to a constant, we essentially arrive to two different ordinary differential equations. But each of them will have also conditions attached to them. So before I write these equations separately, let's see what happens when we plug in this product format of the solution into all initial and boundary conditions, right? So once you plug it into the PDE and separate it, the next step is to actually plug in this format of the solution into all conditions in the problem. And well, I should say into all homogeneous conditions. This one will be dealt with at the end, the non-homogeneous one. So now we're going to plug in y of xt equal big X times big T into all homogeneous boundary conditions. So there's three of them if you look carefully here. So I have yt of x0 equals 0, y of 0t equals 0, y of pi t equals 0. Now, remember, you always take the partial derivative and then you plug in. So yt of little xt is going to be big X of little x, t prime of little t. Then I can plug it in here. So that means at time t equals 0, this condition becomes big X of little x, t prime of 0 equals 0. You got to be careful to do this correctly when you plug in this format, this solution. Y of 0t is going to be big X of 0, big T of little t equals 0. And then finally the last one, x of pi, big T of little t equals 0. So once again, all we did, we just plugged in the product format of the solution into all homogeneous boundary conditions. Always remember, we're looking for non-trivial solutions. If the first condition, x of x, t prime of 0 equals 0, if this is true for any x, then it must follow that t prime of 0 must be 0. Right? I mean, if big X of little x varies, so presumably some of them are non-zero, obviously, because you're looking for non-zero solution, then t prime of 0 must be 0. By the same token, in the second case, as t varies, the only way for this second equation, second condition to be true for any little t is for big X of 0 to be 0. Because again, t of little t can be non-zero. And by the same token, the last one, if it is true for any t, then big X of pi should be 0. Okay, so let's look again to the separated form with minus lambda and the conditions in big T and big X. So notice that now the problem splits into two ordinary differential equations together with various conditions. So let's write the first one in big X. So one of them will be a boundary value problem, basically. So the first one, x double prime of little x over big X of little x equals minus lambda with the conditions x of 0 equals 0, x of pi equals 0. So this will be basically a boundary value problem in big X. And it's also homogeneous. But it's an ordinary differential equation. So a boundary value problem for a single variable function. And the other one will be an initial value problem in big T. So T double prime over big T of little t equals minus lambda, together with the initial condition T prime of 0 equals 0. So typically what happens, you split the function, you obtain an equation which is a boundary value problem in big X, and an initial value problem for big T of little t. So the special one to begin with is this boundary value problem in big X. This boundary value problem is called the Sturm-Liouville problem by the name of mathematicians involved in this theory. And for reasons that will be apparent a little bit later in this presentation, this is also called the eigenvalue problem. So you'll see as we move along with the material that lots of different problems will have essentially similar or the same type of boundary value problems that appear in this step of the operation. Solving this type of equations sometimes is also called the Sturm-Liouville theory, because there are generalizations of this, which we might talk about later, maybe. All right, so before we move on to the second page, because we're going to basically solve these two separately, we're going to start with the boundary value problem, with the eigenvalue problem. Let's summarize what we had on this page. So we separated the PDE. That led us to two different ordinary differential equations, each of which is attached to conditions that come from the original boundary conditions, the homogeneous boundary conditions. So the three boundary conditions we had gave us boundary conditions for big X, and in this case an initial condition for big T. And we call the boundary value problem in big X the Sturm-Liouville problem. And we're going to start solving that one first. So stay tuned for the next page. All right, so let's continue. I copy what we had at the end of the page previously. Now, notice that the ODE involved here, it's actually pretty straightforward. It's the second order ODE with constant coefficients from what you learn in ordinary differential equations. And by the way, at this point, if there is no risk of confusion, you can basically write just big X, because it's clear when you solve this problem that it's just function of little x. So, you can multiply by big X. So then you get x double prime equals minus lambda x, which means if you move it to the left hand side, we get x double prime plus lambda x equals 0. And again, the boundary conditions x of 0, x of pi equals 0. All right, now notice we don't know what lambda is. So in order to solve this ODE, we need to come up with the characteristic equation, which is r squared plus lambda. At this point, you may look at the formula for the solution of the second order ODE with constant coefficients. There is no x prime, so the characteristic equation is just r squared plus lambda. But the nature of the solution depends on whether this equation has real or complex roots. So we need to actually take all cases, although you'll see only one of them leads to non-trivial solutions. So let's start with case number 1, the case when lambda is less than 0. Again, for aesthetic purposes, let me denote in this case lambda by minus a squared. Because I'm going to take a radical, so it's so nice to actually have a streamlined format of the solution. So any negative constant can be written by minus a squared, right? Minus a positive number. So in this case, if lambda is less than 0, then the equation r squared plus lambda becomes r squared minus a squared. And if it is equal to 0, then you have the roots plus minus a. So two distinct real roots, minus a and a. So the solution, then it's a combination of exponentials. Again, have the formula in front of you just to see where that comes from if you forget. So it's c1 e to the ax plus c2 e to the minus ax. But remember, we have boundary conditions. And remember, a boundary value problem may have infinitely many solutions, a single solution, or no solution at all. There's no way to tell until we actually impose the boundary conditions. So we need to plug in 0 and pi. So we're going to plug in a 0 first. So x of 0 is c1 e to the a times 0 plus c2 e to the minus a times 0. So c1 plus c2 is going to be equal to 0. And then we're going to plug in pi. So that gives me c1 e to the a times pi plus c2 e to the minus a times pi equal to 0 again. We need to solve for c1 and c2. Let's get c2 in terms of c1. So c2 is minus c1. We can plug it in here. So we get c1 e to the a times pi minus c1 e to the minus a times pi equals 0. We can pull out c1. But at this point, notice that since this is not equal to 0, that means c1 is equal to 0. And if c is equal to 0, c1 is equal to 0, then from the substitution, c2 equal to 0 as well. So that means the only solution is x of little x equals 0. So that's the trivial solution. So no non-trivial solution in this case. So this case doesn't give me any solution that I'm looking for. We're looking for non-zero solutions, remember. And I hope you see why actually we took a minus lambda, because as you might guess, lambda will be positive. That's the only case in this particular situation that will give me non-trivial solutions. And so this case, for example, will be skipped later once we end up with the same Sturm-Liouville problem. So for example, from this point on, if we have, again, the same problem, we're not going to do the case one more time. We know that doesn't lead to non-trivial solutions. There's an intermediate case, lambda equals 0. Well, when lambda is equal to 0, the format for the solution in that case, lambda equals 0, that means x double prime is 0. That means x, if you double integrate it, is going to be c1 plus c2x. A linear term. Once again, let's plug in the boundary conditions. X of 0 is 0. That gives me c1 plus c2 times 0 equals 0. c1 equals 0. X of pi, c1 plus c2 times pi must be 0. But because c1 is 0, this is c2 times pi equals 0. And that gives me c2 equals 0 as well. No solution either in this case. All right. Finally, case number 3. We're going to leave now lambda. We're not going to make any renotation for now. We're going to make another renotation later. But let's just say now that lambda is a positive number. And in this case, the characteristic equation gives me complex roots. See, if lambda is positive, when you move it to the right-hand side, that's actually plus minus I square root of lambda. Yeah, I mean, imagine like lambda is 4, so that'll be plus minus 2i. So you have complex roots, and in that case, the solution for big X is c1 cosine of square root of lambda x plus c2 sine of square root of lambda x. It's a combination of cosine and sine. I hope the Fourier series starts to smell a little bit. And you'll see immediately how they actually kind of suggest you'll end up with such a thing. But let's be patient. Again, all in due course. All right, just like before, we're going to plug in the boundary conditions. So x of 0 must be 0, x of pi must be 0. X of 0 is c1 cosine of square root of lambda times 0 plus c2 sine square root of lambda 0 equals 0. And then the same with pi for x. All right, now cosine of 0 is 1. So this thing is 1, sine of 0 is 0. So the first equation gives me again c1 equals 0. All right, c1 equals 0. And then the second equation, because c1 is 0, I can get rid of this. From the second equation, I must assume c2 is not equal to 0. So that is one of the key steps in the problem. So pay attention here. Remember, we're looking for non-trivial solutions, right? Clearly, c1 0, c2 0 both work. But again, that'll give me again the trivial solution. C1 must be 0 from the first equation. There's no other way around. But on the second equation, I must assume C2 is not 0. And then I look to see if there is such a lambda, right? Because we still don't know what lambda is, such that I have C2 non-zero. Because if C2 is 0, of course, that's the trivial solution. So the question is, can I find lambda such that the second equation, sine of square root of lambda pi is 0, so that I can still maintain C2 not being equal to 0. Again, we're looking for non-trivial solutions. So it boils down to the question, do we have values for lambda such that sine of square root of lambda pi is equal to 0? And the good news is that not only we have such values, we have actually infinitely many of them. Look at the unit circle here and notice that any multiple of pi will give you sine equal to 0. 0, pi, 2 pi, 3 pi, and so on. So square root of lambda pi must be a multiple of pi. And you can write that multiple of pi in the form of n times pi with n from 1, 2, 3, and so on. Not 0. Remember, we're not looking for 0. Lambda must be strictly positive. So any non-zero multiple of pi. So at this moment, not only we found lambda, but we found infinitely many of them, given by these multiples of pi. And what is actually lambda equal to? Well, we can cancel the pi. We can take the square on both sides, and it turns out that lambda is equal to n squared. And the corresponding constant C2, you can name it now a constant that depends on n. So let's call it big AN, for example. Because it depends on n, right? Imagine basically that you have for each lambda a constant corresponding to it, right? I mean, you have C2 sine of square root of lambda pi. Since you have lambda being either 1 squared, 2 squared, 3 squared, 4 squared, and so on, the corresponding constant can also be denoted by A1, A2, and A2, AN, and so on. Those constants must be found at some point later, obviously, but we'll do that later, actually. We'll do that actually later on in the process, toward the end. So for now, let's focus on the fact that we found lambda to be n squared. And let's see, the corresponding big X, you can actually label it by n, xn, to be sine of nx. So actually, we're going to deal actually with this notation later. So let's forget about that one. Let's just denote the actual solution corresponding to sine of square root of lambda pi, right? So because lambda is n squared, sine of square root of lambda pi, sine of square root of lambda x actually is going to be sine of nx. I'm going to write it down one more time on the second page to put it all together before we continue. So stay tuned. All right, so let's review what we just got here. Forget about C2. I got a little bit confused with C2. C2 will be dealt with at the end when we reassemble the solution. So for now, just focused on square root of lambda, right? So again, from the previous page, we concluded that the solution of the Sturm-Liouville problem that gives me non-zero solutions will be in this format, C1 cosine of root lambda x plus C2 sine of root lambda x. And the only case that gives me non-zero solutions is the one that involves C1 equals 0. So that's what we got from the previous case. And for C2 to not be equal to 0, we must have square root of lambda pi equal n pi, which gives me lambda equals n squared, which is the reason why we typically call these lambdas indexed by n. And notice that for each lambda, so lambda n equals n squared, and for each lambda we have basically a corresponding solution of the Sturm-Liouville problem. Because root lambda becomes n, so you have basically sine of nx, and that solution can be again indexed by little n. So essentially you found infinitely many solutions of the Sturm-Liouville problem. In this step, you found the lambdas and the corresponding xn's. I mean the corresponding solutions of the boundary value problem. Each of these lambdas that you found are called eigenvalues, and the corresponding function is called the Eigen Function. And again, it's important to understand that each of them come together. I mean, both come together for each n, 1, 2, 3, and so on. So for each value of n, you have a pair of an eigenvalue and an eigenfunction. And keep in mind that essentially gives you infinitely many solutions of the Sturm-Liouville problem. And that's, for now, just half of the general solution. Remember, y of little xt is assumed to be a product between big X and little t and big T. And all we did for now, we just found half of the problem, right, corresponding to big X. All right, so at this point, you move to the initial value problem. And for each eigenvalue, we're going to solve the initial value problem in big T. And the initial value problem in big T, if you remember, was T double prime over big T equals minus lambda, big T of little t, right? And again now, and the other condition attached to it was T prime of 0 equals 0. And we can write it in a single line. If you multiply by big T, T double prime plus lambda big T equals 0. T prime of 0 equals 0. Now notice lambda is known at this point from the previous part of the problem. Now you don't take all cases, right? I mean negative, positive, and so on. Now lambda must be equal to n squared because that's the conclusion from the Sturm-Liouville problem. So we solve now basically for each lambda this boundary value problem, this initial value problem. And basically you have a solution for big T corresponding for each eigenvalue. So now we can replace lambda with n squared. And the coefficients of the solution, because the characteristic equation gives you complex roots again. So r is plus minus in if you take the radical. But the constants that are involved in solving this big T, you can now index them by little n as well. Because again, they depend on n. You solve this for each n. So this is going to be some constant. We're going to call it an cosine of nt plus some other constant bn sine of nt. We still have to find an and bn from the remaining conditions to be imposed. So remember, in the formula, usually you write C1 and C2, but at this point, we write it in terms of n because we have essentially each instant of these equations for each n. And in fact, you can call the solution itself Tn. You can index it by little n right now since you have one for each value of n. The remaining part is to figure out these values of an and bn. So let's see, we still have a condition to deal with, t prime of 0 equals 0. So we need to differentiate big T first. So that gives me minus nan sine of nt plus nbn cosine of nt. Replace t with 0. That gives me minus an sine of 0 plus nbn cosine of 0, which must be equal to 0. This is 0 because of sine of 0, and cosine of 0 is 1, and bn equals 0, that means bn is equal to 0. We're getting closer to the finish line, believe it or not, and bn 0, that means tn of little t is an cosine of nt. That's all we could say at this stage in the game. So let's do another summary. Sturmoville problem gave me a bunch of eigenvalues, which in turn gave me a bunch of eigenfunctions. Each eigenfunction is going to be just half of the solution of the wave equation. For each eigenvalue, I'm going to solve the problem in big T. For each eigenvalue, we get here at the end a corresponding function for big T, which gives me the second piece of the solution. So right now, if you notice here, we basically found infinitely many solutions of the PDE, of the boundary value of the PDE, that satisfy all conditions except the remaining one, which is the initial displacement. Remember, we still didn't deal with this one, the initial displacement. But we have infinitely many solutions, and we can index them as well. So we have yn of little xt. We have xn times t, and I'm going to start with an, cosine of nt, and then sine of nx. Right? So the big X times big T. All right, so here is finally the beauty of the method, or if you wanted, the whole point of dealing with Fourier series up until this point. We have infinitely many solutions. All of them satisfy all homogeneous conditions, right? I mean, if I plug in 0 for x, this is going to be 0. If I plug in pi for x, this is going to be 0. It will satisfy the PDE. That's where it came from, right? We separated the PDE. All conditions are satisfied except the last one, the initial condition. No matter which n you pick, if I plug in 0 for t, an sine of nx obviously is not going to be equal to x. So none of them satisfies the last remaining condition. However, remember that x, the function which denotes the initial displacement, can be written in terms of series, in particular in this case Fourier series, and this is where the saving grace comes essentially. And also the superposition principle. So basically we have infinitely many solutions already found. By the superposition principle, then a linear combination of these is also a solution. So summation from 1 to infinity of an cosine of nt sine of nx is also a solution. The only thing that needs to be found is these series of coefficients such that the remaining condition is satisfied. Well, let's impose that condition. What do I need to happen? Well, I need, again, this will be my final solution basically, y of xt, right? I need y of x0. That is to say, I need the summation from 1 to infinity, an cosine of n times 0 sine of nx to actually be equal to x. This is what I need. Now, cosine of n0 is 1 in this case. So everything boils down to the question, can I find these coefficients, an such that the summation from 1 to infinity an sine of nx is equal to x? Well, that is another way of asking, can you find the Fourier sine series for x? And hopefully for everybody in this class at this point, the answer is a resounding yes, we can get it from the table. So pause if you need to grasp everything that went up until this point, and let's finalize the problem on the last page. All right, so I just wrote what we had on the previous page. The problem, the main assumption that the solution is separable in this format, and what we achieved, that the solution can be written in terms of a series. Each of the component of this series, each term here is a solution of the PDE because it's linear and homogeneous. A linear combination is also a solution. The last question is to fit the non-homogeneous part. This is where the series play a role, right? So if I want y of x0 to be equal to x, on one hand, y of x0, if I replace t with 0, gives me a summation of an sine of nx, and I need this to be equal to x, because that's the initial condition. I should also mention, I need that to be equal on the interval 0 pi. That's also important, right? I mean, the length of that vibrating string. So the very last moment, and we'll see, we're going to repeat this until people get used to the whole process, because we have plenty of example. The last question you usually have in the process of solving a boundary value problem using this method is, now it's time to assemble the solution in the form of a series, and now it's time to finally deal with the non-homogeneous condition. And usually that entails setting up a series to be equal to the function that represents that condition. So then the solution can be found insofar you are able to get the function in the condition in the problem in terms of a series necessary that comes from the Sturm-Liouville problem, right? Those Eigen functions will play a role essentially in coming up with this series at the end. So in this case, it's essentially asking about a Fourier series, a Fourier sine series, for the function x in the interval 0 pi. If you have the table, you get it from the table. If you don't have the table, you use the definition for the Fourier coefficients, right? So 2 over pi, the integral from 0 to pi, x sine of nx dx. Fortunately, in this case, we can use it from the table. So we know that in the table, x as a Fourier series, Fourier sine series is 2 summation from 1 to infinity minus 1 to the n plus 1 over n sine of nx. So the series you have that came from the problem must match x, which in turn is given by its corresponding series. So you basically claim victory and claim that you found the solution of the problem when you can find what an is, those remaining coefficients. So just match the left and right. Don't forget the 2 outside the summation. So an is 2 minus 1 to the n plus 1 over n. Normally, if you get to this point, I give full credit. Technically, to actually really be correct and have the full solution written, just for final satisfaction, so to speak, once you find what an is, you need to go back and plug it into the actual solution of the PDE. So the full solution of the PDE, of the boundary value problem, in terms of a series of functions, is an, which we just found, cosine of nt, sine of nx. All right, so I hope people don't get too scared right now, because we're not going to stay that long for all problems. We will focus on various aspects. We will do full problems from top to finish, for sure. But once we get acquainted with the whole process, some of these steps are taken for granted. In particular, the solutions of the Sturm-Liouville problem, we can get it from the table as well, from some formulas, if it's the same as the one we solved before. We're going to comment a little bit on this later, and I'll show you how this actually relates to the general equation, the traveling waves, if you're curious about that. But I think that's it for today.